All right, let's talk about the hidden math that quietly runs our entire modern world. It's called numerical analysis. And really, it's the science of finding a good enough answer to problems that are just, well, they're so ridiculously complex that a perfect answer doesn't even exist.
So let me ask you a question. Think about designing a new airplane, trying to model the global financial market, or even just predicting if you'll need an umbrella tomorrow. What's the one thing that connects all of these massive challenges?
The answer? None of them can be boiled down to a single neat little equation. It's just not possible. The real world is messy, it's complicated, and so these incredibly important fields, they have to rely on a different way of thinking, a way to get an answer that isn't technically perfect, but is so unbelievably close that it might as well be.
And that gets us right to the heart of the problem. You see, there's this huge gap between the beautiful, perfect world of math on a blackboard and the chaotic, messy reality of the problems we actually need to solve.
So you've really got two ways to find an answer. On one hand, you have the analytical solution. That's your E equals mc squared. It's perfect, it's elegant, it's always true. But the thing is, for most real-world problems, it just doesn't exist. So we have to turn to the other option, the numerical solution. This isn't a formula, it's a process. A super clever, step-by-step recipe that gets us closer and closer to the true answer until we're practically on top of it.
But you see, the second we agree to an approximate answer, we have to start talking about something called error. And managing error isn't some flaw in the process. No, it's the absolute foundation that makes all of this work. It's how we know we can trust the answers we get.
Okay, so first up we have round-off error. You can basically think of this as the computer's fault. Your computer, no matter how powerful, has a limited amount of memory. It can't store a number like pi with all of its infinite digits. It has to round it off somewhere. And every single time it does that, a tiny, tiny error creeps in.
The other kind is called truncation error. Now this one is different. This one is a choice we make on purpose. Imagine you're trying to describe a perfect smooth curve. That's an infinite process. So what do? We approximate it with a bunch of short, straight lines. We truncate the infinite complexity. And the small difference between our straight line approximation and the real curve, that's our truncation error.
Now, you might be thinking, okay, so the goal is to get rid of both of these errors, right? Well, not exactly. And here's the catch. These two types of error are in a constant tug of war. Trying to crush one often makes the other one explode.
Let's look at an example. Say we try to get our truncation error super low by making our approximation steps, that little h, incredibly tiny. We use millions of tiny straight lines to map our curve. Sounds good, right? Our approximation is now amazing. But now the computer has to do millions, maybe billions of calculations, and with every single calculation, a tiny bit of round-off error is added. Pretty soon, those tiny errors pile up into this massive, unavoidable problem that completely swamps the error we were trying to fix in the first place.
So the most accurate answer, the best answer, isn't found by making our steps infinitely small. It's actually found at a sweet spot, some intermediate step size, where the truncation error going down meets the round-off error going up. The goal here isn't perfection. It's all about finding that optimal balance. To really see this in action, let's stage a little competition. The challenge is simple. Find the root of an equation. That's just the spot where the function hits 0. We've got 3 different algorithms, all competing in what we'll call the algorithm race to 0. And here are our racers. In lane 1, we've got the bisection method. It's slow, it's steady, but it is guaranteed to get to the finish line. In lane 2, Newton's method. This one is the speed demon, incredibly fast, but it's a bit of a risk. And in lane 3, the secant method, a really clever mix that tries to give us the best of both.
So how are we going to pick a winner? Well, it's not just about raw speed. The true measure of how good an algorithm is something called the efficiency index. It's the ultimate balance between how fast an algorithm closes in on the answer and how much work, how much computational sweat it has to put in at every single step. First up to be judged is bisection. It's totally safe, super reliable, it'll always get you an answer. But its efficiency index? A flat 1.0. It does the job, sure, but it's not breaking any records. It kind of just plods along to the finish line. Next up, Newton's method. I mean, its speed is incredible. The number of correct digits can literally double with every single step. But there's a price. It's a gas guzzler.
It requires 2 expensive calculations for every step it takes, which brings its efficiency index down to about 1.414. Blazing fast, yes, but very costly.
And the winner of our race is the secant method. With an efficiency index of 1.618, the golden ratio, how cool is that? It hits the absolute perfect sweet spot. It's almost as fast as Newton's method, but it's way smarter about it, cutting its cost per step in half. It is, without a doubt, the practical, efficient champion.
Okay, so that race was just for one little problem. But the real mind-blowing power of these ideas comes when we scale them up. I mean, way, way up. What happens when you have to solve systems with millions of equations all tangled together? And I am not exaggerating. A modern simulation, whether it's for airflow over a wing or the structural integrity of a bridge, can easily have over 1 million equations that all depend on each other and all have to be solved at the exact same time. The scale is just staggering.
You can't just attack this with the math you learned in high school. A direct, brute force solution would literally take centuries to run, even on our best supercomputers today. The amount of work required just explodes. It's impossible.
So again, we have a choice. On one side, you have direct methods. They're precise, but their cost grows exponentially, making them completely useless for these huge problems. On the other side, you have iterative methods. They're way more efficient, especially for the kinds of problems you find in physics. But their speed, their very ability to work, depends entirely on the condition of the problem. Basically a score of how difficult and sensitive it is. So what do you do if you're handed one of these really nasty, ill-conditioned problems? Well, this is where the real art comes in. Experts use a technique called preconditioning. It's like a mathematical judo move. You take your impossibly hard problem, you apply this clever transformation to it, and you flip it into a brand new, easy problem that your iterative method can solve in a flash. It's not just about making things faster. Often, it's the only way to get an answer at all.
You know, as we've seen again and again here, numerical analysis isn't really about finding one perfect tool for every job. It's really the science of making smart, strategic trade-offs. Every single decision is a balancing act. Do you want something that's guaranteed to work, or something that's super fast but a little risky? Do you need incredible accuracy, even if it's going to cost a fortune in computer time? It's all about weighing simplicity against power, precision against stability. It's a game of choices. So I'll leave you with this final thought. In this world we live in, a world completely driven by data and complexity, perfect, clean answers are almost always out of reach. So maybe the best possible answer is actually way more valuable than a perfect one we can never find.